Hello, my name is Makabi. I am a student at長岡University of Technology. Today, I'd like to talk to you about the study we have been doing. And the title of the presentation is Computing Word Similarity Between Nouns Using Common Sense Knowledge. Okay, let's start. First, let me give you some background for our study. To develop an intelligent computer, we not only need grammatical knowledge, but also a large amount of common sense knowledge. For example, in a conversational system, we need some knowledge such as my dog means to pet dog in order to appropriately respond to users' remarks such as I was playing with my dog. To construct such system, many researchers have focused on methods for building common sense knowledge bases and providing their accessible representations for using in natural language processing tasks. I introduce some related works. In the artificial intelligence field, the common sense knowledge base is also called upper ontology. The upper ontology is an ontology which contains many general concepts. For example, a collection of a book has a concept of a type of information-bearing object of the form of paper. Sumo and Psych are instances of upper ontologies. The study using upper ontologies can exploit rigorously defined common sense knowledge. However, the knowledge representation that is defined by an upper ontology cannot be matched fully with actual expressions. Compared to this, the concept net defined the common sense knowledge as some relations are added to sentences or words. For example, capable of relation connects the concepts of dog to common sense knowledge such as walk, sleep, and so on. It is better suited to natural language processing tasks than the upper ontology. But the Japanese concept net, the most of concepts are collected manually. Therefore, the coverage of common sense knowledge is exceptionally low. In this study, we aim to solve these problems. We define the noun as a concepts and predicates that are modified by a concept as common sense knowledge. The predicate that we are referring to here is set of verb, adjective, and Japanese verbal noun that is modified by a concept with Japanese case particle. For example, when predicate of bark and to train are modified by a concept of dog, the predicate becomes common sense knowledge of dog. As a final goal, we collect a large amount of common sense knowledge from web text, and we aim to automatically construct common sense knowledge base that can be utilized for semantic analysis in NLP. We compute a similarity between concepts and use it as a relation. For example, concepts of dog and cat have a similar predicates, so they are similar concepts. I will explain a construction process of common sense knowledge base. First, we select appropriate noun as concepts. We select about 12,000 nouns that are labeled as concrete noun in the Goitaike as a concepts. The Goitaike is the largest Japanese thesaurus which contains categorized noun basis of semantic classifications. Next, we select appropriate predicates as common sense knowledge. To select common sense knowledge, we made 3 hypotheses about the specific properties of common sense knowledge. First, the predicate P signifies the common sense knowledge about the concept C when P are frequently modified by C in sentences. For example, when a sentence of I cross the road is frequently occurred in the predicate of cross is common sense knowledge of road with high probability. On the basis of this hypothesis, we sorted a predicate based on the number of predicates that were modified by the concept. The list shows the top 10 predicates adding to the concept road. The predicate placed upper in the list are considered more appropriate as common sense knowledge. However, when we think along the basis of hypothesis, some predicates which cannot characterize the concepts are added as common sense knowledge. Such predicates are generic predicates and modified by many concepts. Therefore, we define the second hypothesis. The predicate P, which are modified by too many concepts, is not the appropriate common sense knowledge. For example, the predicate use is incorrect common sense knowledge of road. We will delete such predicate from corrected set of common sense knowledge. The graph shows the emergence distribution in the top 10,000 predicates. It is displayed on the double logarithmic scale. The part shown by straight line presents a per approximated curve to data. The part shown by upper left point presents that predicates modified by concepts are more than 35,000. For example, predicate of to become obstructed and B withdraw something fall under the point. Compared to this, the part shown by lower right point presents that predicate modified by too many concepts are in a minority. For example, predicate of either and are fall under the point. What I mean is that the predicate modified by many concepts, it means that generic predicates are found in right side of the graph. We focused on the scope which is out of the per approximated curve. The predicates which fall under the scope are modified by too many concepts. So we delete the predicate belong to scope as deleting predicate. For the last, the third hypothesis, whether the predicate P is common sense knowledge or not, depends on number of unique concepts modified in P. Predicate which is modified by many concepts, it means generic predicates become common sense knowledge in some concepts which modified in only a few predicates. For example, the predicate run could not characterize the concept person, which frequently modifies many predicates, but it could characterize the runner, which modified by only a few predicates. It means that concepts modified in many predicates increasing the number of predicates to be deleted. We investigated the emergency distribution in the top n predicates that are modified by concepts. As a result, the number of deleting predicates decreases with increasing n. In accordance with our expectation, concepts modified in many predicates increasing the number of predicates to be deleted. We use the equation of approximated curve to calculate the number of predicates that were deleted. Note that when n is smaller than 1000, the number of deleting predicates was 234. We compute a transactional predicate selection at this point. We consider the result of predicate selection. The list shows the top 10 predicates adding to a concept road. The left list shows the baseline using only a frequency information. Compared to this, the right list shows the approach results. Approach method can delete the general predicates and can assign the appropriate predicates to upper in the list. Therefore, it is effective that approach method deleted incorrect predicates using statistical information. Last, we compute similarity between concepts. To compute similarity, we made two hypotheses about the specific properties between concepts. First hypothesis, concepts are similar when common sense knowledge sets for the concepts are also similar. We take concepts of cat and dog for example. On the basis of hypothesis, if both of concepts are similar, common sense knowledge sets for them are also similar. Therefore, we can calculate the similarity between concepts for using similarity between common sense knowledge sets for them. Second hypothesis, if concepts C1 and C2 are similar and concepts C2 and C3 are similar, then concepts C1 and C3 are also similar. In brief, the similarity computation between concepts holds a transitive relation. We think about a hypothesis in using example of cat and dog. If cat and dog are similar and cat and rabbit are similar, then dog and rabbit are also similar. It means that if both of concepts are similar, there is a correlation between them. So we use the correlation coefficient as similarity score between concepts. We delete common sense knowledge with frequency lower than NWI. NWI is the lowest frequency of shared common sense knowledge in WI. WI means the word I. This made it possible to delete common sense knowledge that had a lower frequency and should have been classified as noise. For example, the known pair of dog and cat is shared common sense knowledge, such as to keep, live with, like, and die. And die and like are the lowest frequency of shared common sense knowledge in dog and cat, respectively. Therefore, we deleted inappropriate common sense knowledge with frequency which was lower than lowest frequency of shared common sense knowledge in each known, such as to take for a walk, bite, and play with. We compute the transaction of similarity computation and at this point. So we use the top 1,617 nouns as an evaluation set and calculate a correlation coefficient between the correct set and each set. We compare approach to two baselines. Baseline 1, we do not delete any predicate, just use a weighted predicate based on frequency. Baseline 2, we delete some of predicates whose point-wise mutual information PMI score are similar than threshold. Method is proposed by Aizawa. We measure the path between nouns in the Goitaike and use them as a correct sets of word similarities. We use the Jaccard similarity, Simpson similarity, and weighted Jaccard similarity as similarity functions. The graph shows the evaluation result of similarity computation. Approach received the highest rating for accuracy and best score on the basis of the Jaccard similarity. Therefore, our approach is independent of similarity functions. The table shows an example of assigned common sense knowledge adding to concepts. Our approach was able to assign appropriate common sense knowledge, such as the dog is kept and we move through the world. The table shows the pair of concepts with high similarity. As a result, we confirm that if concepts have similarity common sense knowledge sets, their concepts are also similar. In this study, we obtained about 35,000 common sense knowledge. Our knowledge base size is about 3 times as large as ConceptNet. Okay, conclusion. In this study, we automatically constructed a large amount of common sense knowledge that can be utilized in many NLP tasks. And we automatically obtained about 35,000 common sense knowledge. Moreover, We selected appropriate predicate as common sense knowledge using statistical information. Then, we confirmed that our approach was able to collect a higher number of appropriate common sense knowledge. And we compute similarity between concepts based on their common sense knowledge set similarities. The method is able to compute similarity between concepts more effectively than existing methods. Thank you for listening.